Good morning. Yeah, it's still morning. This is ECE 637, Digital Image Processing 1. And today we're going to pick up on the continuous space and time Fourier transform, particularly the continuous space. But I also want to do some quick things over the labs. I understand that the labs are a little bit, how do I put it in a nice way? In flux, okay? But because I'm trying to make this transition from MATLAB to Python, so I'm sort of offering you both options. But I think probably all things being equal, if you don't mind, it's probably better off. So if you submit the MATLAB according to traditional instructions, that's terrific. But if you try to do the Python one, it's probably better because you probably learn more valuable material. Okay, but either way is fine. But we're trying to keep up with doing some revisions, and then the revised versions, there'll probably be bugs and errors and things. So just let us know when there are, and we'll try to make corrections and updates. But yeah, it's like what they say, in the shopping mall when they have a thing. Pardon our appearance, but we're trying to make it better, kind of a thing. So okay, so let me. Okay, this is obviously not good. Uh, yeah, okay. It's a little bit hard to gauge because it's flipped. Oh, yeah. Let me move it over a little further. It's too bad they didn't make this silly thing bigger. You know what? They need to find some engineers. Okay. Okay. All right. Engineering. Engineering is a wonderful thing because well, at least helps make the world go round. Somebody's got to know how to actually make things work. So, uh, we talked last time. We were talking about the continuous space Fourier transform, and this is it. Hopefully, oh, I know one thing I needed to do. There was, like I said, a friend of mine, actually from Georgia Tech, made up some lectures for the undergraduate signal processing course on YouTube. I wanted to distribute those because I haven't looked at them myself, so I can't fully endorse them. But he's a solid guy, and Aaron Lanterman, and you could probably just Google his name and find them. So if you're not familiar with the Fourier transform, that might be a resource you could tap. But I'm sure you could also Google stuff and find lecture videos online. All kinds of resources. I understand mathematically this may not be super intuitive if you haven't seen it before. In fact, it's probably not intuitive at all if you haven't seen it before. But the idea is that you decompose the signal in terms of its frequency components. The essential concept is that any signal with it in some sense of approximation, which is pretty strong, can be represented as a sum of sine waves at different frequencies. And in the most general case, it's like an infinite, uncountably infinite set of sine waves. And that's what the Fourier transform is, just decomposition in sine waves. And then here you're like reconstructing it by putting the sine waves back together to form the signal. So this should be an inversion. And if the function f is well behaved, then this will be an exact inverse to that. By well behaved, I mean it has to have certain properties like be continuous and so forth. So okay, so and then u represents frequency in the horizontal direction, and v represents frequency in the vertical direction, and yeah, so we went through that kind of fast. This is the 2D Fourier transform. When you rotate, a sinc maps to a rect maps to a sinc. So this rectangular function has a Fourier transform which looks like a sinc. It's actually a 2D sinc. This 2D sinc is not rotationally symmetric, but the rect isn't rotationally symmetric, so you wouldn't expect them to be. And the 2D Fourier transform has the property that if you take the signal and you rotate it, then its Fourier transform also rotates. That kind of makes sense, I think. So it's isotropic. The transform is isotropic. It's not invariant to rotation. So in a particular case, this, and then there's this properties. There's the property. There's this property. The property, which is a little more general than just rotation. But if you take, so here what you're interpreting is that x and y are the coordinates in space. You pass it through a matrix, a 2x2 matrix transform. One particular case is that matrix could be a rotation matrix, but it doesn't have to be. It just has to be invertible. And then the Fourier transform of this distorted or rotated or whatever function is given by this form here, where now u and v multiply on the left by the matrix inverse A. So A has to be invertible. And then there's a scaling function here. So a special case of this is this idea of stretching and scaling in one, stretching and compressing in 1D. So as I said before, if you take a signal in 1D and you stretch it, the frequencies go down. So stretching in time corresponds to compression in frequency. And compression in time will make the frequencies go up. So that corresponds to stretching in frequency. So they go in opposite directions. Just remember that they're opposite, okay? And that way you can always figure out what the answer is. So, but this, in a particular case where A is, say, a diagonal matrix identity times a scalar, then this corresponds to stretching and compression. But also, if A is orthonormal, then here's a key thing to remember, because we will use it. Okay, this is a rotation matrix here. That may seem familiar. You can derive the rotation matrix. Let me just do this stuff real fast, because it's all good stuff, because you use it all the time. Like if you rotate, so you have, this is a unit vector, right? So this is x, and this is y. So that's 1, right? So if you rotate your coordinate system by theta, this will be like this, right? So that's of length 1, and this is theta, right? And let's see, so that will be like, hold on, yeah, so the idea is that, I can draw a line like this, and I can draw a line like that, right? And that will be sine theta, right? And this will be, I'm sorry, this is cosine theta, and this is sine theta, right? So what that means is that I have, if a rotation transform is like this, so we have like 1, 0, right? That has to come out to what? Well, it has to come out to, the x-coordinate is cosine theta, so this will be cosine theta, and that will be sine theta, right? Because I messed that up. Shoot, it's true, but my logic is wrong. This is sine theta. Okay? And the reason is if I multiply this vector by this matrix, that will be cosine theta will be here, and sine theta will be there. Does that make sense? And then, if I switch my logic and I put it like this, then I can draw a second diagram for that. Okay, and that's theta. And then this thing will be minus sine theta, and that will be cosine theta, right? So then this will be minus sine theta, and this will be cosine theta. Now you might say, but it's wrong because I got the minus signs flop. Well, it depends on whether you're talking about a clockwise or counterclockwise rotation. And it depends on whether you're talking about the input or the output, okay? They're both orthonormal. It actually turns out that there's another thing you can do. You could also, okay, this matrix is what's called then orthonormal. So orthonormal means means that you have A is a matrix, and you have like, you know, E1, E2 like this, right? And let's say it's EK. Let's say it's a square matrix, okay? Orthonormal means that for all I and j, that the inner product, so I, EJ, so that's the inner product. The other way I can write the inner product, in this class, we don't use that kind of notation. This is more like physics notation, which is fine, but it's just not the notation we use. So we use EI transpose EJ. That's the same thing. It's going to be the inner product, right? And that's going to be equal to delta I minus j. Because, so what does that mean? That means it's 0 for I not equal to j, and 1 for I equal to j. Because what it means is that, obviously, if the inner product of any column vector with itself is 1, that means it's normal, okay? It's of unit length, that means normal. But it's orthogonal because the inner product with any column with any other column is 0. Okay, so that's what happens when you have an orthonormal coordinate system. The coordinates are orthogonal, they're perpendicular, and they're of unit length, okay? So orthonormal. So for an orthonormal matrix, it's easy to show that A transpose A is equal to I. Oh, not I, it's I, right? It's also easy to show that A transpose is equal to I, okay? So basically, A transpose is equal to A inverse. So in this special case of orthonormal matrices, the transpose is the same as the inverse. It's important to keep that in mind, especially if you're an electrical engineer, because electrical engineers believe deep in their soul, and it's important to be aware of this belief because it's false, okay? Some things people believe are not true, okay? I mean, just because you believe something doesn't make it true, okay? So you believe that all transforms are orthonormal, okay? I'm sorry, unless you're a special electrical engineer, you believe that because you've been taught all your life, where all your life started in your freshman year, that all the transforms you paid any attention to, you spent all your time on, were all orthonormal. The Fourier transform is orthonormal. At least it's orthogonal. Sometimes it's not normalized. The FFT is orthonormal. All these transforms are orthonormal. So you have this tendency deep in your soul to believe that the transpose or the adjoint of a transform is its inverse. But that's not true in general, okay? So it's important to be aware of that natural bias, okay? Because if you're in communications, for example, the transpose operator is what's called a match filter. The match filter has certain optimality properties, but it's not the inverse, okay? And later on, in the next few lectures, we'll learn about tomography. And in tomography, there's this thing called a back projection, okay? And it seems like the reverse of the forward projection, and it is kind of, but it's not the inverse. You can't, and it's interesting, in the very early days of tomography, that's one of the ways they tried to invert the transform by just taking its transpose, but it doesn't invert it, okay? You get something, but it's not right, okay? So that's an important thing to keep aware of. So orthonormal transforms are very important. We're going to be using them a lot. So this is orthonormal so that you can show that using the orthonormality of the transform that the rotation in space corresponds to a rotation in frequency. And that's what this is, okay? So that's rotated, rotated. We're going to use that in a little bit. Now, this circ function, which we call jank here. It's not super standard notation, but this comes up a lot because in optics particularly, because lenses usually have circular apertures. And it's going to turn out that, roughly speaking, that the lens, the electromagnetic wave at what's called the aperture, or the pupil, sometimes they call it, is more or less. Notice I like to throw the words more or less in, because if I say more or less, or kind of, it's an indication that what I'm saying after that, regardless of what I say, it's true. Because I put like a caveat. But it's more or less the Fourier transform of the actually image at the surface of the imaging device. So the lens is in the Fourier domain, and the image is in the space domain. So because of that relationship, the aperture in the lens will create a point spread function on the surface of the image, which is essentially, that's another one of those qualifying words, essentially this, okay? It's actually not this, because this goes negative. So what it ends up being is the energy, so it's this squared, okay? So, but this function comes up because it's a point spread function of an ideal optics, optical camera, conventional optical camera. I have to bring my camera in sometimes. It's fun to play with. Okay, remind me. I have two things I have to bring in. One is my camera, and then there's this other thing I like to play with every year, which is like a little 2D sampling function that I bought at a children's museum. So, okay, now I want to build up your intuition. For a continuous space Fourier transform, a plane wave. So what does it mean to be, I know what a sinusoid is in 1D. I know what a single unit frequency is in 1D. It's a sine wave, right? With some phase and amplitude. A cosine wave is a sine wave. It's just a sine wave with a different phase, okay? So the question is, well, what are essentially eigenfunctions? What are the individual frequencies in 2D? Well, I can answer that question by saying, well, okay, a pure frequency should be an impulse at some frequency. So this is an impulse at frequency U0, V0. So if I take the inverse Fourier transform, I plug it into the inverse Fourier transform equation. Let me zoom in on this. I basically just, whenever I integrate a delta function against anything, I just evaluate that function at the location of the delta function, which is U0, V0. So I just plug U0, V0 in for U and V, and I get this. So this is a pure complex sinusoid in 2D. Now, real signals are, remember I said they're always conjugate symmetric. So in 2D, if I have a Fourier transform, so if I have like f of f, if I flip it in frequency by putting a minus sign there, and I take the complex conjugate, I get f of f. I know that notation is unfortunate. Maybe I should call this G. So for real signals, real valued signals, they're always conjugate symmetric. So that means that the amplitude is symmetric, and the phase is sort of conjugate symmetric. So it's going to be like the phase is going to have the property that G of f equals minus the phase of G of minus f. So the phase is antisymmetric, and the amplitude and the magnitude is symmetric. Okay, now that's fine in 1D, but in 2D, it gets a little more complicated, and it can be a little counterintuitive. So So you'll have u and v here. Okay. What happens is that I'm like anticipating the natural error that people will make. It's a very common error. It's very, it's kind of an obvious thing to do that's false. Okay, that if you take a point here, call that, so we'll call that u0, v0. It's conjugate symmetric, not with the point here or the point here. It's with here. So this is minus u0 minus v0. So you got to flip across both axes. So the other way of looking at it is that you kind of reflect around the center of the coordinate system, right? So that's important because I'm telling you, you'll naturally have a tendency to think that it's conjugate symmetric this way. That's not true, and it's not true that it's conjugate symmetric this way. You got to flip this way, okay? So, so with that in mind, then in order to get a real value signal, this is complex. The real valued version, we got to add the conjugate symmetric part that reflected around the center of the coordinate system. Hold on. So we take e to the j, these frequencies, and then e to the j, the minus of those frequencies. Now, by the way, okay, I know you're graduate students and everything, but I also know that people tend to forget this stuff. So I'm going to go over it real fast. That you have, you have like e to the j omega is equal to cosine of omega minus j times, plus j times the sine of omega. You know that's true because if you draw this coordinate system, e to the j omega looks like this. It's a unit vector. This is real and this is imaginary. It's a unit vector with angle omega. In fact, I could have made that a theta. Maybe that would be more intuitive. Okay, so the imaginary component is going to be the sine, and the real component is the cosine. Okay, so from this I can calculate that it's easy enough to show that the cosine. Oh, so I take e to the minus j omega. That's going to be the cosine of omega minus j times the sine of omega. Why? Because sine is antisymmetric and cosine is symmetric. So if I take the negative, the cosine doesn't change, but the sine reverses sine. Okay. So if I add those two together, okay, and then I divide by 2, I get the relationship that the cosine of omega is equal to e to the j omega plus e to the minus j omega over 2. So you don't have to remember this formula. Okay, you can just derive it. It's really simple. And if I subtract the 2, I get that the sine of theta of omega is equal to, so if I subtract them, I get, hold on. Right, so I'm going to get, then I get, I get that the sine is equal to e to the j omega plus e to the j omega. Hold on, did I do that over 2j? Is that right? I'm doing the algebra in my head, so it's easy to make a mistake.
E to the minus j.
Oh, right, yeah, okay. And then, oh, yes, thank you. It always makes me feel better when the students correct me, because then I know that they're following what I'm saying, okay? So the point is that you can derive this stuff, okay? I know for a lot of you this is very, very remedial, but it doesn't hurt because even for some of you, it might be rusty. So you get, so then the inverse Fourier transform of this is going to be this cosine. So for real valued signals, which we're usually dealing with real valued signals because you can't actually display a complex valued signal in a simple way. So they're usually real valued. And okay, so the intuition then is like this. That let's see. So this is in the space domain, and this is the frequency. So basically, you have so a complex sinusoid looks, a real valued sinusoid looks like this. The phase will be so the phase is all 0 for these examples, but the you can think of it like a wave in the ocean, although you can't tell whether the wave's going this way or this way, okay? But you can think of it as a wave in the ocean. The point is that the direction that the wave is heading, so perpendicular to the stripes, is like this, right? So you're going to get two dots, one associated, that's the high frequency, you might say, and that's its negative frequency. That's the positive and negative frequency. You can say, well, where's that dot coming from? Very good question. Because, well, you can't really have a negative signal if you're plotting it, okay? Because if it's controlling the, the intensity of the light. We'll talk about this later because you can't have negative light. So you have to have a DC pedestal component. So that's the DC component, okay? It didn't show up in our calculation because we were allowing for the possibility of negative values. And now what's going to happen is if I rotate one of these, the other one will also rotate. The other thing that's true is if I stretch these, okay, then I'm reducing the frequency, so these things will get closer together. So stretching here, again, causes these to contract. And contracting these will cause these to stretch, okay? So it looks like this. Okay, so here, that frequency is obviously lower because the spacing is large. The period here is larger, so the frequency is lower. Okay, so these are closer together. Oh, no, actually they're supposed to be the same. Oh, never mind. Here. There, that's definitely lower. Okay, so they're closer together. And it's higher frequencies that are further apart. And then there's some geometric relationships between these. So if the period's P0, and these are sort of intuitive and sometimes, like there are a lot of things like this that they're intuitive and then sometimes you'll blink your eyes and then you can't remember why they're true anymore. So you kind of have to go over them, think through them, get used to it. But P0 is the period. So the 1 over the period in space will be the frequency. So that'll be the distance from the origin in the frequency component. And then this angle phi will correspond to that angle. I tried to describe that already. And then there's some other relationships here. Oh, one thing that's interesting is that as the wave, so if you have a wave, because this does come up, you have a wave, so this is x and this is y. Okay? Let's say you have a wave and it's just tilted at a slight angle relative to the coordinates. Okay. Well, then what will happen is this distance here, the period that way is relatively small, but the period this way is longer. Does that make sense? Okay, because, and if you tilt it close enough, this period will get longer and longer and longer. Okay, that actually has effects because what it means is that it's like a sort of a moire effect, and so that comes up in these equations. So U0 is the period as you hit this axis, and it corresponds to 1 over this distance in the frequency. So in frequency, what would happen is that this would be like here. So that would be, so this is U and that's V. So this frequency along the horizontal direction would be very low as, oh, I drew the thing on the wrong side. Oh, shoot. Okay, it's really supposed to be here. Ignore this little dot. So this frequency is low because, and then as this thing tilts closer and closer, this gets closer and closer, and then the frequency becomes lower, and that corresponds to this period being long. Okay, so think about that until it makes sense to you. Now, let's see. Oh, rep and okay, there's this thing called repetition. So the repetition of a signal in time is, think of it as an operator. So if you have some signal X and you apply the rep with period T, you just replicate it at some period T. Now, hopefully, the signal has the property that it's some, it could be that you took this signal and maybe it doesn't decay. So then summing this infinite sum is just going to blow up. But assuming that this thing sort of decays away at a rapid enough pace, when you take these and sum them together, it'll just look like a periodic signal. And its period will always be t. It could have other periods, like for instance, it has a period of 2t, that's for sure. And it can even have a period of less than t, like t over 2. But it will always have a period of t. Okay? So that's called rep. Now, because this signal is periodic, you'd say, well, the Fourier transform is defined as an integral. The Fourier transform is defined as an integral. F of t times e to the j 2 pi ft dt. Now, if you go back to your calculus, when you compute an integral, okay, it turns out that if you compute an integral, let's say the integral of g of t dt, for this integral to be well defined, for this thing is called absolutely integrable if, when you have a definition, if means if and only if, okay? It's just a convention. So it's really if and only if the integral of the absolute value of g of t dt is less than infinity. So most integrals we'd like to deal with should be absolutely integrable. In other words, the total absolute area under the curve is finite. If that's not true, then it's very disturbing, because it turns out that you would certainly expect that if you have an integral, let's say this is some kind of function, okay, and you integrate it, and you would certainly expect that if you integrated little pieces of it and then added them up, you should get the same answer, right? I mean, like let's say integrated from 0 to 1 and from 1 to 2 and 2 to 3. You integrated it over every unit interval and you sum those together, you should get the same answer as if you should get the same answer regardless of what order you sum those intervals, right? It'd be like if somebody was delivering milk to your house and somehow the order in which they delivered the cartons changed the amount of milk, okay? That would be disturbing, physically unrealistic. But here's the disturbing thing. If the function is not absolutely integrable, you can you can break the integral into pieces, add them together, and get any answer you want, okay? You can get any answer. So you can pick any number. You can say 17. Yep, can't do that. Okay, any number. So there's something deeply disturbing about that if you can get any answer you want. Nonetheless, we do integration with not absolutely integrable functions all the time, okay? But I just want to make you aware that it's kind of a little bit sketchy, as my son would say. So it's kind of sketchy when it's not absolutely, and in particular, the sinc function is not absolutely integrable. We know it's not absolutely integrable because it drops off as 1 over t, and we know that the integral of 1 over t is not integrable, right? Everybody knows that. So I just want to warn you that there's some sketchy stuff going on here, okay? It's been made rigorous by mathematicians, thank you very much, but, we're not covering all that details. So this function is definitely not absolutely integrable because it doesn't decay. But we can still take its Fourier transform. It's sort of befitting that since the function doesn't, since its integral is messed up, that its Fourier transform is also messed up. It's formed by delta functions. And delta functions, as you recall, aren't in functions. So it seems appropriate that a function that can't be integrated results in a result that isn't a function. Okay, but in any case, that's a detail, I guess. So there's this other thing called a comb. A comb is, if you've ever had a comb for combing your hair, you know what a comb is. And I think these little things on the comb actually have a name, but now that these days, it used to be I could say pretty much anything I wanted up here and get away with it, but now people can Google it and find out whether it's true. But maybe the things on a cone are like called times or something. So this comb actually has a shape to it, though. They're not all the same length. So, and their height of the impulses are modulated by the signal. So the way we do that is when we take a comb, we take x of t, and we multiply, we modulate each impulse at each location, the kth location where the impulses are separated by spacing t. We modulate them by x of t. Okay, and you can write that expression two ways. They're exactly equivalent. One is that you can take the delta function. You can take x of t inside the sum, or you can take it outside. It's not a function of k, so it doesn't care. So the one way of thinking about it is you're just taking sort of the flat comb with the equally length times, and you're modulating their amplitude. And this is the thing I like to demo. I have like this thing, this bed of nails toy that's sort of fun to play with that I got at the Children's Museum. You should remind me to bring it in. So this is a key. Now, the thing here is that this is kind of fundamental because it's a way of representing this continuous time signal with a set of discrete impulses. Now, this is still a continuous time signal, but it clearly is encoding discrete informations, the samples of the values of the function at each corresponding point. And it raises a question, can we reconstruct this continuous time signal from these discrete samples? And the answer is going to turn out to be yes in certain cases when the frequencies in this signal are limited, sufficiently limited. And what that means is that if the frequencies are sufficiently limited, it means that this function is sufficiently smooth. So if the samples are sufficiently close together, then you're going to be able to recover the shape of this function from these discrete samples. Okay? And I always like to say that, like, for instance, in MATLAB, or I guess now in Python, whenever you want to plot a function, you usually evaluate the function at about 100 points. Because usually that's enough points to get, the shape of the function properly. But if the function varies very rapidly, you may need to take more samples. Okay, now, rep and comb in the frequency domain. So the key thing here is this. If you have a signal, and you apply the comb function to it, then in the transform domain, it's equivalent to applying the rep in the transform. And through duality principle, a rep in time corresponds to a comb in frequency. So what does this mean? And then the same thing's true in 2D. Only it becomes a 2D rep. There's a 2D rep and there's a 2D comb. And then there's a same transform pair. So a comb in time in space corresponds to a rep in frequency. And a rep in frequency corresponds to a comb in space. So what does this mean? It means that if you have a signal that's periodic in space or time, its Fourier transform will have a comb structure in frequency. And if you sample a signal, but with a comb in time or space, the Fourier transform will have a repetitive structure in frequency. This is going to be really important. So I want to kind of go through these fast, and I'm hoping that maybe you can do them on your own largely, because I also want to touch on some of the computer stuff. And but basically, this just is some quick exercises you can work through to understand how you can use what I've just gone over to take the Fourier transform to some common signals that arise. Okay, so let's say you have a function. This is kind of a drawing of a function. Okay, which is, it looks like a 2x4 coming out of the plane. So I'm trying to draw the height of the signal, and it's basically like a rect along the x dimension, but it's invariant along y, so it's constant along y. So you can think of this as a 1D function, or you can think of it as a 2D function, but it's constant in y. So if I take if you think of it as a 2D function, this function is separable because it's a function of x times a function of y. The function of y is just 1. So if I take the Fourier transform, what's the Fourier transform of rect? Everybody should know this. Like you fall out of bed in the morning, you should be able to say sinc, right? Rect goes to sinc, sinc goes to rect, okay? So the Fourier transform of the rect is the sinc. What's the Fourier transform of 1? Delta. So this is going to be a sinc times a delta. But the sinc is in U, and the delta is in B. So I like to say, I mean, I don't mean this to be like overly aggressive, but it's like, I mean, but they're happy things too. Razor blades are useful tools. So think of this as a spatially modulated razor blade edge, okay? Okay, so, okay. So it goes up and down with the shape of a sinc. Because it's the razor blade being like the delta function, okay? So here, if I have a delta function, this is sort of like just a razor blade coming out along the horizontal direction, vertical direction. So the razor blade is sort of vertically oriented. That's like a delta times 1. If I take its Fourier transform, the Fourier transform of the delta becomes 1, and the Fourier transform of 1 becomes the delta. So it actually just flips it. Because if you think about it, going along horizontally, this has got a lot of high frequencies in it because it varies very rapidly. So that way it goes out to very high frequencies. But going along this direction, it's constant. So it doesn't, right, yes, it's constant. So yeah, it doesn't have a lot of high frequencies. Everything's concentrated at the DC frequency. Oh, for non-electrical engineers, DC refers to direct current, okay? Which is sort of legacy terminology. It's the zero frequency. Okay, same thing here. Okay, now what you have is you apply, this is like this, except for you now have a rep. You're doing a rep to the rectangle because the rectangle is repeating with period x, where x is the spacing. So a rep in space corresponds to a comb in time, in frequency. So here you have rep x. The dividing by a modulates the width of the 2x4. Okay. So this is like a this is a rep of a rec. So the Fourier transform of that is going to be the comb of a sinc, because the rec goes to a sinc, and the rep goes to a comb. Wow, did that make any sense? Okay, okay, good. Thank goodness. Okay, and then the Fourier transform of the 1 is delta, so you get the same kind of deal. Okay, you can think about these. I'm kind of going through them fast because I want to touch on a few other things. Now you can also window this thing. You can window this thing. So this is like this, but you see those 3 dots, the ellipses, indicate that it continues on to infinity. Now the alternative is that we window it to a finite window. In practice, everything is always windowed to a finite window on a computer because you can't really process things to go to infinity. So B here is assumed to be large compared to A or X. Okay? And so what happens now, and F is the F from the previous problem. See, F is the F from the previous problem. So now when you multiply this window by F, what happens is multiplication in space corresponds to convolution in frequency. So and the Fourier transform of this rec is going to be a sinc. So you're basically going to convolve this with a little sinc function. So the shape of these tiny, so this is maybe not drawn the best, but it tries to convey the idea that what were these were little impulses, they're little arrows. They get replaced by tiny little sinc functions. And the width of those sinc functions corresponds to 1 over B. B is big because it's a window, so 1 over B is small. Okay? See, big goes to small. That's a key idea. Stretching goes to contraction, big goes to small. Now, we could also do the window vertically. In that case, what happens is that the sinc functions now are oriented vertically rather than horizontally. If we windowed both ways, by the way, we would get little 2D sincs. And now this is the example I wanted to show from that I want to bring the toy in that's sort of fun to play with. That what if we have this periodic rect in 2D recs? Then the 2D rep, so this periodic extension of these little squares, is a rep in 2D. That 2D rep corresponds to a 2D cone. So now what we do is we get a bed of nails. Each of these impulses is like a nail pointing up, and the height of that nail is modulated by the Fourier transform of one of these tiny things, okay? So the small things in space correspond to the big things in frequency, and the big things in space correspond to the small things in frequency. That's the thing you have to remember. Big goes to small, small goes to big, stretching goes to compression, big opposites. And then finally, if we put a window, then you get these little sync functions instead of nails. So instead of having a little nail at each point, which is a 2D impulse, you instead approximate the impulse by a little sync. And the size of the sync is proportional to 1 over the size of the window. So if the window is really big, the sync gets really small. So it's actually 2 syncs here. There's a big envelope of the sync associated with the size of the small thing, and then there's the little sync corresponding to the big window, right? It's easy to get confused on this stuff, even when you've done it for a long time. You got to keep in mind, the best way to sort out things is anything that's big in space is small in frequency, okay? Now, I want to do this thing. If there's just 3 minutes, and maybe I could just do it really fast, over to my computer, if that's possible, if we could switch. This is great. If we could switch to the computer, maybe. Oh, am I plugged in? Yeah. Oh, no, I'm not plugged in. That's the problem. Okay, it's my fault. Sorry. There you go. I'm plugged in. I got 3 minutes. This is like a 5-minute warning in football or something. Okay. So I'll make this bigger so we can see. Okay, okay, so here's the thing. Purdue courses 637. Okay, so this is the web page for the class. I added a link here. Where is it? Oh yeah. Okay, so physics-based, MATLAB-based laboratories. So I added a link. This is the things, and you can do them this way, okay? So don't worry, that's fine. But if you want to work on the newer laboratories that we're working on, so these are the Python-based laboratories under construction, you'll take to a web page that looks similar but is different, okay? Now, I put here, now the thing is, some of you may not be familiar with how to do some of this stuff, but here is instructions that Scott Dye was kind enough to contribute. They're in the Piazza, but I captured them here so that they wouldn't disappear in the future. So that's information on how to configure your Windows machine to do like bash shells and things that I talked to you about previously. This is some instructions, very rough instructions, of how to install similar things on OS X for the Mac. That's easier because Mac is based on Unix to start off with, so the stuff is mostly there. Oh, one thing I think I said is, you should get the GCC compiler with Homebrew. You can read this, Git, and okay, that's good. Now, there was something, Xterm, Term 2. One of the things that you should definitely get is this thing called Term 2. It's much better, okay, than what Apple could do. And now, Anaconda, that gets a little more complicated, and basically we just pointed you to where you could go look, okay? So you need to install this thing called Anaconda. I mean, actually, you don't have to have it, but I strongly recommend it. And it helps you manage your environment. With one of the beauties of Python is that you can install different packages, and they play well together. But Anaconda allows you to switch between different package configurations for different applications. Okay, and then we're running out of time, so I'll probably have to pick this up next time. But then you'll need an ASCII editor. I gave you some suggestions, okay? then next time what I want to do is, so in here this procedure gives you instructions. One of the things is that I'm out of time, but there's this environment.yaml file that you'll need to use. I'll show you how to do that next time. So thanks a lot, and we'll see you on Wednesday. Take care. Bye.